It is undoubtedly true that we are made of information. In that case, if it's information, can't we go back to the past?
Does that mean returning the quantum to its arrangement?
That's how it is.
In theory, that might be the case, but it becomes a hassle.
Well, I think someone will come up with a way to do it without it being a hassle. You see, when Einstein came up with the theory of relativity, no one believed him.
Are you saying there is no analog in this world?
That's how it is. The presence of a minimum unit means that there is no analog. I realize that I need to change my thinking here a bit, because I believe that information is infinite, so it's different from matter. I've talked before about how it can create various dimensions and such. Based on this, the information is also discrete and has stages. Conversely, if even information isn't like that, it wouldn't make sense. But honestly, I felt a little lonely. I realized there that it's not about escaping the universe, but that we can't escape death, because we are the space itself. When the universe contracts, disappears once, and then bounces back, it resets at that stage. Immortality is impossible, it seems. For now, at least. That's how it turned out. But, well, I guess there's some kind of plan. Something, you know. This is addressing the question of how to explain an empty space. There is always something in a space. That itself is the universe. However, there is still something there after all. Or is there not? Is it zero? That is exactly it. Can someone tell me about that? The black hole explodes. Space-time does not exist. The world we see is created by our perception. The universe was a world governed solely by information. We might be looking at the average value of a set of discrete probabilities. I would like to delve a little into the concept of the smallest unit in the world. When considering the smallest unit in the world, the first question that arises is whether matter can be infinitely divided, right? You might think that by breaking it down into smaller parts, it can go on infinitely. You would assume it should be possible to do so infinitely. If it were actually possible to divide things infinitely, then something like a smallest unit wouldn't exist, so there would be no room for debate. In response to this question, a philosopher named Democritus provided a rational answer as early as 2,300 years ago. The result of dividing something is dimensions and size, right? As long as those remain, you can't say it's been divided infinitely. Since it's still there, it can be divided, right? This hasn't been divided. On the other hand, let's say hypothetically that it had already been divided by someone. Let's say I have prepared something by saying, I divided it. Since it's divided, the divided pieces should have no dimensions and should be points. There are no dimensions. It is a point. Alright, let's gather the points and restore them. Gather them. Can this be done? There's no mass. Zero. No matter how much you collect, zero is zero. So, it can't be restored. Therefore, something that has been divided infinitely cannot be restored. This is where a contradiction arises. Therefore, Democritus concluded that it is inconceivable for matter to be composed of things that are originally of size zero. This conclusion was reached 2,300 years ago. In modern science, the prevailing idea is that matter has a minimum size. It is undoubtedly true that the smallest units of matter and space are finite. Therefore, this time, I would like to proceed with the discussion under the assumption that the smallest units of matter and space are finite. General theory of relativity. Albert Einstein. The initially announced theory of special relativity is the principle of the constancy of the speed of light. In a vacuum, light travels at the same speed in any inertial frame. That's what it's saying. And also, the principle of relativity. All inertial reference frames are equivalent. Next, I will present the general theory of relativity. It is a theory that connects time and space. Dr. Einstein actually developed the theory of relativity when he was 25 years old. And at the same time, he calculated the dimensions, the size, of atoms, something that no one had been able to answer for 2,300 years. Dr. Einstein proved that matter is made up of particles that have size. Next, regarding quantum theory. Quantum theory, unlike the theory of relativity, is a theory that was, so to speak, developed from experimental results. Quantum theory was first formulated in 1900 with the creation of the initial equation of quantum theory by the physicist Max Planck's quantum hypothesis. Planck is the person who advocated for the quantization in physics. Quantization refers to interpreting physical phenomena not as continuous quantities, but rather as discrete, separate collections of particles. Planck is the person who perceived energy as being like particles, and discovered that it is related to their frequency and behavior. And then, it was actually Albert Einstein who realized that there are phenomena that exist which are related to that frequency and behavior. Einstein tried to prove that light is truly made up of particles. Light is not continuously distributed in space, but is composed of a finite number of energy quanta scattered throughout space. Later, Einstein explained it using the light quantum hypothesis. Until then, the prevailing view was that the electromagnetic field of light was a wave. Quantum mechanics has already become indispensable in our everyday lives. Semiconductors used in computers are made based on the theory of quantum mechanics. For example, things like DVDs, lasers, digital cameras, and smartphones would not exist without the theory of quantum mechanics. It is said that more than 35% of the GDP of developed countries is generated using technologies based on quantum mechanics. About half of it consists of things that simply cannot be made without quantum mechanics. It can be said that modern life cannot exist without quantum mechanics. Throughout history, the theory of quantum mechanics has consistently produced results. It has not been wrong. In short, the experimental results so far are consistent with the theoretical values. Whether something is correct or not, science basically cannot prove it. However, it is widely acknowledged that these two are extremely reliable physical theories. Time is a fundamental concept for recognizing events and changes. Without a doubt, we can feel the passage of time. Our recognition of time as a number comes from Newtonian mechanics, I suppose. For example, Newtonian mechanics tells us how things change over time. It's precisely because we have the concept of time that we can predict what will happen in the future based on what has happened in the past, isn't it? In the history of science, the first person to probably formulate physical laws into equations was Galileo. Galileo's equation describes how the height of an object changes over time. It was also Galileo who made the accurate pendulum clock. The time it takes for the same pendulum to swing once is the same, isn't it? The person who discovered this was Galileo Galilei. However, it wasn't as simple as it might seem. It's about how Galileo discovered the law of the pendulum. Galileo, it seems, would count his own pulse while watching the chandeliers, which looked like candle holders with candles standing on them, swaying in churches and such. He investigated how many times his pulse would beat with each swing of the pendulum. Then I realized that it's the same every time. However, when you think about it, this story is a bit strange. The question is, how did Galileo know that the time it takes for a pulse to beat is constant? That's the point here. The conversation is like, you found out through the pendulum, right? In short, they use the pulse to verify that the pendulum is regular. And then, to verify that the pulse is regular, they use the pendulum. This is what's called circular reasoning. What this means is that whether you're measuring time with a pendulum or measuring the time of a heartbeat, you are not actually measuring time itself. I'd like to touch a little on the claim that time does not exist here. Even before the concept of time was established, humanity was building civilizations, and not being able to measure time accurately didn't particularly hinder daily life. For example, there were plenty of rough methods to measure things like the position of the sun or the size of shadows. It's just that people didn't consider those as time. However, equations that unfold over time, like Newtonian mechanics. In Newtonian mechanics, time always comes into play. So if there were no concept of time, Newtonian mechanics wouldn't be applicable. In our world, we first have a large flow called time, and within that system, we believe that changes in physics and changes in things occur. However, the reality is that, judging from the method Galileo used to measure time, we can only measure how one thing changes in relation to another. This is what we can understand from the current discussion. We can certainly feel the passage of time itself, but it is more accurate to understand that we gain a secondary sense of time through comparisons between events, such as a pendulum swinging once while a heartbeat occurs 5 times. Therefore, the concept of time is not a mechanism that forms the center of all things. Rather, for living beings, it is a concept that is somewhat optional or not essential. you can realize that it is simply a word that represents a relationship. There is now a theory called quantum gravity theory that quantizes the interaction of gravity. This quantum gravity theory is highly anticipated as a theory that unifies both general relativity and quantum mechanics. It is said to be a key to understanding the fundamental concepts of physics, time, space, matter, and force in a unified way, and is also considered one of the most important challenges in physics. The world described by this so-called quantum gravity theory is one where the space that contains the world and the time that orders the occurrence of events do not exist. The theory suggests that in our world there is only the process of constant interaction between the quanta of space and matter. Therefore, it posits that there is neither time nor space. Everything, including all of you, is sustained solely by the interactions of these tiny particles. It's the simplest reason. In the current physical theories like this, space refers to a place where there is nothing, right? There is a concept called quantum of space, which is the idea that space itself is made up of quanta, or in other words, a collection of particles. Therefore, in this quantum gravity theory, space is considered as a quantum. Space itself is a quantum. For example, in our perception, you could say it's the sense of Newtonian mechanics. When you throw a crumpled piece of paper into a trash can, the paper bounces a bit after being tossed into the can, right? This is the way objects collide and continue for only a limited time. However, when dealing with this phenomenon in quantum gravity theory, the time and space we know are merely concepts that arise from the interactions between quantum particles. Therefore, in the process of throwing a piece of paper into this trash can, it is necessary to consider space and time themselves as part of the process. Based on our previous theory, we only needed to calculate the trajectory of this piece of paper, the strength of the trash can, and the rebound when they collided. However, in the case of quantum gravity theory, we have to calculate everything, including space itself. Everything is quantum. Please listen with that kind of understanding. Therefore, time and space are different in order within the quantum realm, aren't they? What is being said is that the quantum interactions occurring in the process themselves are space itself. You are considering that space itself is filled with quanta, aren't you? It's not that an object is going inside there. The space itself is entirely made up of quanta, so each individual quantum is just changing its expression. There's an LCD screen, right? All the dots on an LCD screen are fixed, aren't they? They don't move, do they? However, when the picture of the ball being thrown blinks and moves, the white part also blinks and moves, doesn't it? A similar feeling to that, as if that screen were a space. That's the kind of theory it is.
I see.
That's why only the quantum interaction became just one. That's why things like time and equations aren't included. Naturally, that's the kind of discussion it is. Regarding time and space in quantum gravity theory, as I mentioned earlier, time and space do not exist in quantum gravity theory. I talked about how it might not be a component. Additionally, there is a limit to the smallness and fineness of matter, so it can be said to be finite. Similarly, in quantum mechanics, information is also considered to be finite. If the number of pieces in a jigsaw puzzle is finite, then the combinations themselves are considered information. This also means that it is finite. In quantum mechanics, the exchange of this information and the relationships between the quantum entities themselves are what create what we call space. It's not that there are quanta in space, but rather that quanta are space itself. If you calculate the smallest dimension of a particle that prevents it from being sucked into a black hole, it seems that you can represent the smallest length that exists in the world. This is the quantum scale. The smallest unit, the quantum scale, is called the Planck length. It's something thought up by a person named Planck, isn't it? The Planck length is said to be 10 to the power of minus 33 centimeters. It's hard to tell how much this is. Something like to the power of minus 33 would be extremely small, wouldn't it? You know ping pong balls, right? Let's suppose this represents the size of the universe. Imagine a ping pong ball that's the size of the universe. Then, consider the actual size of this ping pong ball. 1/millionth of that size is the smallest unit, the Planck length. Anyway, it's incredibly small. From the viewpoint of the smallest unit, the size of a ping-pong ball is like the size of the universe. So the image in this quantum gravity theory is that when you look closely down to the extremely small Planck scale, it appears to be like a wave of probabilities composed of different geometric shapes. It is said that the physicist John Wheeler was searching for a way to describe this probability wave. And it seems that this colleague named Bryce DeWitt came up with the idea. The person had an equation for the wave function of space, and based on that, they apparently created a kind of orbital equation related to general relativity. I hardly understood any of it, though. This equation was groundbreaking because it didn't include time as a variable. Most physical equations include time. The theory of quantum gravity is said to not include time, right? It also doesn't include space. These people created equations that do not include time at that time. This was quite a groundbreaking development. However, it was so groundbreaking that most researchers didn't understand how to use this equation. However, researchers also do their best. As a result of further trial and error within that process, something called loop quantum gravity theory came into existence. Well, you can think of this as an improved version. And then there's something called Faraday lines of force. You know how when you place a magnet, there are lots of lines that seem to revolve around it? This is what we call a field. The idea is that there might be something like a field of force lines in gravity as well. It is expressed as a gravitational field. And in this gravitational field, there are things like lines of force. We are beginning to think that everything in the world is quantized. So, the field being used is within the space. It's not that there is space and then the field is there. You could say that a part of the space has become a field. Such lines of magnetic force are not a gravitational field. Rather, the gravitational field is the very structure of space itself. For example, electromagnetic waves. It feels like moving through the space with a pip-pip sound. The concept of magnetism is like this. When you say you are magnetism 2, it is received as magnetism 2, and then passed on as you are magnetism 2 to the next. The you being referred to here is the quantum of space. It's space itself. In the case of quantum gravity theory, space itself is gravity. Space, gravity, and time are unified. That's the way of thinking. The shape is thought to be easy to imagine as being like a soap bubble. The bubbles form a thin film of moisture, creating a surface, kind of like polygons. That's the idea. And then, the points where those lines of force touch are called nodes, and the parts that connect these nodes are called links. The idea is that nodes existing in space have volume, and each one is connected by lines. The lines that are touching each other are called a graph. Essentially, there are points, and they are connected by lines. In the gaps between them, there's something like a membrane, which makes it appear as a surface. In that context, this single unit enclosed by the surface is referred to as a graph. The one enclosed by that surface becomes the smallest unit. It's like a grain of space. The model of space in loop quantum gravity theory looks like this, doesn't it? Therefore, everything is theoretical value and quantum, so it's uncertain. We can't see it. But we think of it as being something like this. Without a model, it cannot be calculated. The term volume within the space mentioned here actually refers to the gravitational field. Space equals gravitational field. In other words, volume is a variable of the gravitational field. A variable refers to a property. It's getting more and more complicated. It's referring to the information about the settings, conditions, or attributes of that gravitational field. Properties. Let's say there is a quantum of space. The attribute of this thing, whether it's red or blue, is the kind of information we're talking about. And the gap and surface dimensions between sections are what we call area, aren't they? The area, like volume, is also a physical variable. From these results, we consider that physical space, being a field, is also made up of quanta. The idea is that a quantum gravitational field, where gravity exists, is also thought to exist due to quanta in the same way. In short, space is also quantum. In other words, it is possible to make the prediction that space itself is also composed of small particles. And then, the quantum states that the space can assume also conform to quantum principles. The behavior of quantum particles is like an unpredictable statistical cloud. Therefore, it can be said that the state of space itself is also discrete. The surface of things like our skin is quite stable. However, when you look at it in detail, it's all made up of probabilities. That's what this is about. Space itself is quantum, and each quantum of space carries information about what kind of quantum the adjacent quantum of space is. For example, let's say I am quantum space A. The producer is quantum space B. Let's say that quantum space B is red. In contrast, I become blue. It's not that I have it. In any case, there's an aspect of being shaped by the surrounding environment. To put it simply, the spectrum of each quantum. It's called the spectrum variable. The spectrum variable changes in correspondence with the spectrum of adjacent quanta, doesn't it? So if the producer turns red, I'll turn blue, and if they turn blue, I'll turn red. That's how it is with space, isn't it? When we talk about a spectrum, it refers to a finite set of options. We call that information. Therefore, the quantum known as space, which is an element that constitutes all things, is always present there, and it changes shape while exchanging information with adjacent quanta. Various substances and elementary particles, as well as spaces that appear to us as a vacuum, are all made up of quanta of space. So a true vacuum does not exist. I initially talked about the idea that time does not exist, didn't I? The probabilistic changes in the microscopic world of quantum space, which constitutes us and this world, are like an average value that represents us in the macroscopic world, the world we see. It's hard to understand each individual detail when looking at averages, but when you look at the big picture, averages tend to be relatively stable, and we are stable. However, when you break it down into finer details, it really is discrete. Therefore, it is clear here that instead of time passing and things changing, the state of things changing itself is defined as time, space-time and fields and particles. Relativity theory considers the world to be made up of these elements, while quantum mechanics suggests that the world might be made up of two components, space-time and quantum fields. After that, there is the term covariance. Covariance refers to the idea of something changing through interaction. The concept is that the world is made up solely of covariant quantum fields, which leads to the theory of quantum gravity. That's why the quantum gravity theory isn't complete yet, but it's quite amazing and a unified theory. Given all that, it turns out that there is no longer the kind of conflict that once existed between general relativity and quantum mechanics. In the past, there was such a conflict. In quantum theory, there are things like the uncertainty principle and probabilities. So, it's called the causality of general relativity, which means that if something starts, you can also know the end. It doesn't change probabilistically along the way. These two were completely separate, but with the development of quantum gravity theory, general relativity, and quantum mechanics have come to complement each other. Looking at history so far, these kinds of things keep happening. The emergence of new theories, by considering the differences between the original theory and a somewhat opposing theory, is indeed the trend we've seen up to now. It doesn't usually come from something completely out of the blue or anything like that. The concept of infinity, which was defined against the backdrop of continuous space in previous physical theories, may have been a hindrance. When you start thinking that things happen continuously, the concept of infinity inevitably arises. In short, it means that it cannot be divided. It is continuous. The existence of continuous time, that is, the existence of concepts like zero and infinity, causes the gravitational force of a black hole to become excessively strong when calculated. The singularity of a black hole, where Einstein's equations no longer hold, will disappear along with the disappearance of the concept of infinity. Therefore, black holes can be fully calculated using Einstein's general theory of relativity. I'll talk a little about the Big Bang. I will provide a brief explanation of how events like the Big Bang and black holes are interpreted through quantum gravity theory. In general relativity, if you reverse time back to the Big Bang, this universe will be infinitely compressed into a point with no volume and disappear. However, If we take quantum gravity theory into consideration, there is a limit to the contraction of the universe, because there is a smallest unit. It will never become zero, absolutely. Therefore, it turns out that there is a limit to the contraction of the universe. It's as if the universe is bouncing back due to a quantum repulsive force. The term quantum repulsive force refers to interactions in quantum theory. Quantum particles attract and repel each other, like magnets. I think you can think of it as the closer you get, the stronger the repulsive force becomes. The result is that the universe, which is in a contraction process, does not shrink to a point with no extent, but instead, the universe will rebound somewhere. According to this theory, it means that a massive explosion occurs, and then it begins to expand again. Could it be that our universe is the result of a similar repulsion? It is expanding now, isn't it? In short, there was a universe before ours, and we are currently in the process where it has contracted tightly and is now rebounding. This possibility has become more likely. The moment of that repulsion is considered the Big Bang. However, it seems that in quantum gravity theory, it is called a Big Bounce instead of a Big Bang. I wonder if it means something like bouncing. This suggests that another universe existed before our universe was born. I would like to talk about black holes next. It is understood both theoretically and observationally that when gravity increases, space and time become compressed. In general relativity, a black hole is a mysterious celestial object where space itself collapses and time completely stops flowing due to the immense gravity. It is formed when a massive star burns out and collapses under its own weight. Currently, several black holes with a mass similar to that of the Sun have been discovered. That's quite large. At the center of the galaxy, there are objects with a mass up to 1,000,000 times that of the Sun. This black hole has a horizon. This is called the event horizon. Inside this horizon, there exists the immense gravity of the black hole. In the current theory of relativity, a black hole is considered to be a point. It's called a singularity. It's a point, but because the gravity is extremely strong, it generates such intense gravity that even light cannot escape from quite a distance beyond the point. That's why beyond that, it's completely dark, and you can't see anything. This is what's called the event horizon. Therefore, once you enter this event horizon, you cannot escape from it unless you travel faster than the speed of light. However, the conclusion was that they couldn't escape because they couldn't reach the speed of light. I went to the event horizon. So, when the producer sees me at the event horizon, what happens to me? It's almost stopped. So, when I return, it feels like tens of thousands of years have passed, even though I was only there for a few seconds. Conversely, from my perspective at the event horizon, I can see time flowing at an incredibly fast pace, spanning hundreds of millions of years in an instant. According to quantum gravity theory, just like the Big Bang we mentioned earlier, black holes also do not become infinitely small. In short, this means that there is no such thing as a singularity. The space compressed by the supergravity of a black hole results in the emergence of a massive pressure from quantum repulsion. This is like the Big Bang. Because it's compressed tightly, a repulsive force comes into play. If I were at the event horizon of a black hole and were to experience its explosion, don't you think? Then, in an instant, it would go boom and explode. From my perspective, it would unfold at an incredible speed, I imagine. However, what happens if we observe a black hole from the outside?
Is it stopped?
It's stopped. It won't explode. The immense gravity of a black hole slows down the flow of time. So from an outside perspective, no matter how much a black hole tries to explode, the flow of time is equivalent to being stopped, so it doesn't explode. Or slow. A slow explosion, taking hundreds of billions of years. In that case, from an outside perspective, there is a strong possibility that the process of repulsion could continue for several billion or even hundreds of billions of years. The black holes that have been discovered so far are actually in the midst of repulsion or explosion, but due to the Rip Van Winkle effect, the explosion is continuing at such a slow pace that we cannot perceive it. Isn't it reasonable to think that way? If we assume that black holes formed in the early universe, and such old black holes exist, some of them may have already exploded. Recently, it turns out that there are radio astronomers who are observing signals from space called fast radio bursts. These are essentially radio bursts that come from various locations in space, about 10,000 times a day, from all directions. This was apparently in such small amounts that it couldn't be detected until now. At present, there are various speculations circulating about the origin of this radio wave. People are saying various things like, isn't that the cause? Or isn't this related to that magnetar? However, it was written in a book I read that this strange radio wave might actually be evidence of a primordial black hole explosion. I think many scholars believe that for physics to take a new step forward, the concept of information will play a fundamental role. In physics, information is defined as a measure of the number of possible choices. We sometimes say analog, don't we? Analog refers to options that have infinite gradations. If we assume that the world we live in actually has a finite number of clear, gradual distinctions, then it is hard not to feel that it is a fairly digital world, based on properties similar to computer bits. The world depicted by quantum gravity theory teaches us that the exchange of information by quanta, which have size and form space, creates this world. To put it in extreme terms, our world might be composed solely of information, with matter never having existed from the start, and perhaps being something insubstantial like ripples on water. We, who are living within it, don't know if it's hundreds of billions of years from now when the universe will contract, but hypothetically, if we were to leave descendants until then. Our descendants, who are one with the universe itself, may not be able to resist the contraction itself, and thus may dissolve into the cloud of probabilities as part of the next universe. The world is moving to the next dimension. You might be the one to open that door.